Okay. Today we going to look into the Deep V3 architecture change. So this is my personal understanding. So there may be some misunderstandings. If there is any during the process, you can just raise and we discuss. Then and during the process, if there's any questions, feel free to ask. Okay. So in DeepSeek V3 architecture, there are 3 changes based on the transformer. So I assume that you guys already have transformer model understanding, right? So there are three changes based on the transformer model. First one is the replacing the feed-forward layer with a mixture of experts. And there's another one is the multi-head attention, which replaced by multi-head latent attention. There's another one is the multi-token prediction. Not sure if you guys had looked before into the DeepSeek V3.
No.
No.
Okay.
Yeah, not yet.
Okay, great. So we will go through one by one. We have looked the high level understanding first. Then if we have time, we go through the code in a higher level. We are not going through debugging through all the code. We're going through the major parts. I already like omit some of the part, only leave the major part that is related to the important concepts. Okay, let's start on the first topic, mixture of experts. Mixture experts, they are previous model that using this already, and there are some I think all of you have heard of mixture model. It's quite simple concepts. So we have the mixture of experts replace the feed-forward network. Feed-forward network, there's only one layer that will be always activated, right, during training and inference. But for MoE, mixture of experts, there are only some of the experts that activate during training and inference process. Right, we have multiple experts, but feed-forward we only have one. Right, we can think of as a single expert, but here we have multiple, and input. Based on the routing selection, we may only select a couple of them or one of them or top K, right? This is the mixture of experts. But previous, mixture of experts has benefit and problems. One benefit is stronger model at lower cost. Because we can have more experts, and because they only activate some of them, so we can train larger models, but we can have similar larger model, but have similar cost as feed-forward because we only activate some of them, right? This is a benefit, but it has problem as well. In a mixture of experts, if we don't have a good routing strategy, it may have node imbalance issue. Node imbalance means that, for example, during the training process, we may only always pick some of them. Some of them are always activated, and others are activated rarely. So only some of them get trained well, right? And others that maybe not trained enough, so it's like it's useless. Some of them may become useless, right? This is one of the issue. So previously, there's one method to control the node imbalance problem. We add a auxiliary loss. This form we can talk about later. But this auxiliary loss is to encourage the node to be balanced. But there's also issue for this auxiliary loss in previous models. For example, if we have this auxiliary loss compose these main parts, and this is the factor to control how much emphasis we put on this balance. So this balance will be added to the main. This loss will be added to the main loss to form the final loss. So if we put too small alpha, this loss may not have much influence, right? So it may not helpful for the node balance controlling, right? But if we put a too large alpha, because it's adding to the main loss, it may affect the main model performance. This is the previous issue that we observed. Any problem with this?
No, I'm following.
Okay. So this is the way that we do that before Deepseek MoE. So in Deepseek MoE, there are a couple of changes here. One is the Deepseek MoE using more experts than previous models. So for the 685B model, it used 256 routed experts. Here in the diagram, this is shared experts. This is routed experts. We will explain later. And there's also an introduction of shared expert for the common knowledge, because we have so many experts, right? It's quite intuitive that we have some overlap knowledge between those experts, right? I think that's the reason DeepSeek pulled out some of experts to become shared experts. so that the common knowledge will be hopefully will be extracted into those shared experts. So let's look at the diagram from the paper. First, the input coming into this MoE model, MoE parts. Then this input will always go to the shared expert, right? This green ones are shared expert, and those blue ones are routed experts. So the input will always go to shared experts. Shared experts will always be picked. But for the routed experts, we only pick a couple of them during training and inference time. We only pick a couple of them, which is based on the weights, how high the score is. We only pick top K, and here the routed experts, they combined by weighted sum. Here you can see the like multiplication, right? It means weighted sum, and finally we'll combine with the shared experts by addition, right? Then coming out, and this dimension is the same as this. Any problem with this diagram?
Oh, good.
Okay. Any problem, please stop me. We try to the sharing, the purpose of sharing to make most of them we try to understand as much as possible together. Okay. So I will split screen into two so that it's easier. So let's understand the formula that used in the paper. So here, UT is the input token. So here the hidden presentation, hidden states equals to the input token plus this is the skip connection part, and this is the share expert, and this part is the routed expert, which maps to shared expert and routed expert. Shared experts it always get activated, right? Like the diagram. And the routed experts only activated based on the gating value. So only some of them get activated. So this gating value, let's look here. So first we have input token, and this is the weight metric. So you multiply weight metric and apply sigmoid, which is normally we do get a score. This score means token to expert affinity score. So it's expert I. This is expert I, right? Here, let's look at here first. We have number of X shared experts. We have R routed experts, right? total of R routed experts. So here I is referred to the routed part because only routed part has the gating value, right?
Yeah.
So I refer to I's routed experts. T means token, current token. So this is affinity score to I's experts. Then based on the affinity score, we pick top K, and others will become 0. So there's no gating value, meaning that some of them are not selected, only in the top K are selected, right? Then this is doing the normalization, which is normally we do for like softmax. Any problem with this part?
Just to summarize that, the input token,
Faham King, seems your voice is quite low.
now, how is it now?
Yeah, it's better.
Okay, I just have to speak closer to, okay. So just to summarize that the input token is going through a list of the shared experts, and these experts are here. It's you've written FFN, so I'm assuming that each expert is a feed-forward network.
Correct.
Right. So yeah. So it goes through. So one input token is now going through the S number of shared feed-forward networks, and
Correct.
then R number of routed. So it gets multiplied by all, but only the top few are selected.
Correct. Only top K.
But
So
every time, yeah,
top K out of R.
out of R, will get selected. But then, okay, top K are getting selected, but the multiplication is happening for the token with each of the expert.
No. This is just the formula representation, but
Oh, okay.
implementation will
In
not go
reality,
through.
okay.
Yeah.
But
Otherwise
without,
we are not
how
safe.
do you, how do you get the gated GIT prime, the value to multiply without actually multiplying all?
Gated value is coming from here. So here is a independent metric that is before this feed forward network.
Oh, that's another metric that is just
Correct.
like a
This metric is created deciding whether
deciding
we
which.
pick.
Okay.
Yeah,
Oh, I
correct.
see now. Okay, thank you for that.
Yeah. Any other problem? Okay. Now we continue. So this is some of modification from the Deepseek MoE. Then there's another one is we mentioned before that auxiliary loss is not that it's not that easy to apply or control. This observed from the previous models. So if we have too much of alpha, it may impact the main model parts. And if we have too small, then it lost the ability to control the balance, right? Load balance. So in DeepSeek V3, they introduce auxiliary law, but called auxiliary loss-free load balancing. So this part it add a bias term, but this bias term does not introduce any like loss term to the main loss. So there is a slight modification to this gating value, which controls the feed forward, right? This score, affinity score, deciding which expert will be picked during this top K process, right? So if we add a bias term, some of them, although originally may not be as high as others, but if we have bias term, we can alter it, right? To make some of them to be picked. Can you guys understand this one?
Not fully. So
Yeah.
after
So for example, we have SI like 0.1 during this process. It will not be picked because there are other like 0.2, 0.3, 0.4. But if we add a higher bias term to 0.1, let it become a higher, like become a 0.5, then it will get selected, right? In top K, right? Quite
so
simple.
okay, so what's happening here is that after you do add the bias term,
Mhm.
the number of selected routed experts increases because
No. We,
no,
we don't increase the number. We alter the selection process. So top K, for example, top K,
mm,
let's say, let's say, expert one got, let's say, this is anonymized. We just say the score, affinity score, for example, is 0.1. E2 is 0.2. E3, E3 is 0.3. And we pick top two. Okay, we pick top two. So this time, E2 and E3 will be picked, right? If we pick a top two, right?
yeah.
Yeah. But before we we get a final SIT value, we add this metric, this weighting metric, this score metric, we add a bias part. For example, we add bias vector to it, so we alter its score, right?
Okay.
Then E1 will get picked, right? Because the final,
I see now.
yeah. It's quite simple. It's just
So
like
it
manually
just
alter.
changes your selection. It changes your original selection. Now
Correct,
you're
correct.
picking different ones than what you were picking before.
Yeah, correct. And you see here the BI will be modified after each batch. It will be modified, but the modification is through our manual modification is not involved in any like gradient chaining. How we do it is quite simple. For example, if we see that the previous batch E1 is not get picked, we just simply alter it a little bit. Like we alter each time, we alter a step size of 0.1. If for example, if let's say here, so E1 will not get picked, right? So next time E1 will add the bias metric for E1 will become something like this. This bias
It's like you give advantage to some
E1.
of the shared shared experts that were not getting picked in the first batch. You just
No, no.
noticed that.
Here we are focusing on the routed expert. The
Oh
shared,
yeah, sorry. Yeah,
yeah,
I forgot. Share. So the shared experts that did not get picked, you look at them and say, hey, this one is not getting picked. Let me give it some head start or some
correct.
advantage. So you put that advantage on, so the chances of that getting picked get increases, and then next
Next
batch.
time, yeah,
Yeah.
become higher. Yeah, yeah. So it's quite simple, simple algorithm. Just manually alter those values so that we balance those experts. Which is the way to solve the previous issue, right? Unbalanced issue, but we are not through
This,
the north, the ordinary north way, right? There's no
mm,
no north term adding to the main model, right?
yep, that's right.
Mm, okay. Those we will look in detail when we look at the code. Okay, so here saying
Maybe just to stop here for a minute, that when we are comparing this to original transformer model, where
correct.
every token has go through a one feed forward network that is just different from all of the others. So if you've got certain amount of tokens, every token is going through a different. Uh, is that right? How does it compare? How does it save
Mm,
computation, or how does it give you more advantage to do it this way in
okay. Okay. So in original transformer, we only have like single expert right here. And it always going through this
yes,
single expert, right?
that is right.
Yeah. Here we have more expert and our final parameter will be much larger than original. But
Yes.
at inference or training time, they are the activated parameters, they are actually can be actually similar. For example, we only pick the shared expert plus 3 of the routed experts, right? Although we have 256 routed expert, but
Mm,
at training or inference time, we always only pick top 3. Then when we count the used perimeter each time is actually similar to the free forward, but we have much larger model, right?
mm, mm,
To learn, but the cost is similar to the original
sorry.
transformer, right?
Yeah, it is. I see what you mean.
Yeah.
But so this is not where we cut a lot of parameters. You don't get any by replacing the original feed forward network from transformer to the
OEM,
yep.
MOE.
What is the yep? What is the advantage then?
Advantage is we have larger model to learn, can learn more,
Mm,
but
okay,
at
I
similar cost.
I see. It just increases the learning
Capacity.
capacity. Yep.
Correct.
So you mean the similar computational cost?
Correct.
Okay. But we do have a lot of experts. They don't care take too much computing cost into the advanced framework.
Sorry, can you say again?
So the current one don't take too much computational cost into the framework. Is that correct?
Yeah, the computation, I think computation is similar. Yeah, computation is similar. You can adjust it to be similar as this. Right.
Or the cost is increased slowly because you still need to calculate some gate or
Correct,
with
correct.
matrix
There are some
multiplication,
addition
something
here.
like
Yeah,
that.
additional complexity, but the feed-forward part will be, I think, is the main cost. This one is relatively small.
So
Mm.
does that mean like multiple expert? Oh, okay. So even the rotated experts number is 250, but it's still small. Okay, compared with one. Okay.
Yeah.
Okay.
So here, auxiliary loss-free node balancing. So we increase, decrease the bias term at the end of each batch, so that to keep the routed expert balanced during the training, right? So this solved the previous problem here. Okay. Next.
So the gamma is just a factor, right?
Gamma is the bias update speed, the like learning rate.
So
No,
in your last equation you written you wrote here. So it's like just
0.0
amplified
yeah, like
amplified factor.
0.1, yeah.
Okay, what if there's no gamma?
Yeah.
Because it's just a amplification, right?
I
Still
didn't put a
factor.
gamma here. There's a gamma in the code. I will show later.
Okay. Okay.
It's a simple like learning rate for the bias.
Okay.
Okay. Okay. Let's go through the high level. This is the diagram from DeepSeek. I draw another one. The high level flow. We go through this high level one before we go through the code. So here is the input, the hidden input, right? Then this hidden input will be reshaped into a batch. Can you guys see my screen clearly here?
Yes.
Okay, great. So it will be reshaped into a batch times sequence and then dimension. Originally is batch sequence dimension, right? So it will be reshaped into a batch time sequence. So there are 2 dimensions here. There are 3 dimensions here. So this input will always go to the shared experts as indicated in the diagram. So it will go through the shared expert always. Then in the routed expert part, which map to this part, in reshaped, then go through a linear layer with a bias. Bias refer to this bias term.
Yep. Just sorry to stop you on the reshaping thing. Your input is the BS. I believe BS is
Yes,
the
batch size, sequence length, and dimension. Yeah, sorry, it's a batch size, BS, batch size.
Okay, go ahead.
So become batch size times sequence length and dimension. So go through here, it becomes, we change it to batch size times sequence, then unrouted experts, for example, 256, right? We apply a linear layer then to get a score. Which means here, right?
That's right.
Yeah, become score. Then we reshape it because there are 256 but in the DeepSeek V3, we divided into groups. There are 8 groups. Then each group, let me calculate, I'm not sure. 256 divided by 8 group. Okay, 32 experts per group, right? So when we shape it, n group and n routed expert per group. So this one, if 256 will become 32, right?
Right.
Yeah. Then we select top 2 group. How we select it? We select by sum of the top 2 expert score in each group. Let's say so we have 8 group. Let's do 3 group here. Inside the group, we have experts, right? Expert 1, expert 2, expert 3, expert 4, expert 5, expert 6. So first we pick decide to pick 2 group. How we pick it? We pick by top 2 expert score. For example, in group 1, E1 and E3, it has higher score. Then we pick these 2 expert score plus together, sum together. So the group score, the group 1 score, score equals E1 score plus E3 score, which is the group 1 score, right? Similar for the group 2, group 3. Then we decide to pick 2 group out of 3 here. Say, yeah, this one, for example, the final score out of these 2 experts become this. Then this one, for example, become this. Then we pick top 2 group that has highest. The group score is summing of top 2 expert score inside that group.
Why do we do it this? Why do we group it and then why don't we just select the top?
Yeah, maybe let me finish the whole thing, and let's talk about later why it does this. So it's not as simple as the diagram shows. There's some more like detail here, right?
Yes.
Let's finish the whole flow. Then we come back why we do this. Okay. So we, based on the sum of the top 2 expert score inside group, we pick 2 group. I think in DeepSeek V3 it picked 2 groups. Okay, then we have the batch times sequence length, then top K groups, top 2 group, right? Now we pick the routed experts within the top 2 group. So top 2 group, I'm not sure, maybe it's pick top 4 group, right? Top 4 group. There are 8 group, but each time it pick top 4 group. So top 4 group will have half of the experts left, right? 128 experts left.
Yes.
Yeah. Then we pick expert from this 128 experts, we finally pick 8 experts out of 128. So the final output here is the activated expert index. So this metric tells us the expert index. Then the activated expert weight, how much weight this expert have, so that eventually when we feed forward through this activated expert, we will do the weighted sum, right? This weight will be used. This index will be used to pick which 8 expert, right? Then going through the final part is to feed forward through those activated expert. Then those are get some weighted together, and eventually this routed expert output and the shared expert get added together and then reshape back to the original shape. Okay. Any problem with the flow?
So this is slightly different from the left diagram where you first, I mean, in terms of how it's implemented, because with the shared experts, first you group them and then you just pick up the top 4 groups out of 8, and then you go do the other thing. So it's like you
no, in the shared part.
Oh, sorry, not shared. I meant routed. I make again. In the routed experts, you do 2 levels of selection. First, you just remove
group
half
selection.
of the group. Group selection, and then first you do at group level, and then you do at expert level. Which in the left diagram, it seems like there's no group.
Correct. This diagram is the detailed implementation.
Sounds good.
Yeah. Okay. So the shared expert here, there's only in the implementation, there's only one, because no matter how many shared expert, you can increase hidden dimension to simulate multiple, right? It's just a feed forward. They are all feed forward, so you can multiply how many share, right?
Yep, correct.
Okay, so the flow doesn't have problem, right? And this is my understanding. The reason that why DeepSeek may be wrong, but all of those, many of those are based on my personal understanding. So if you guys have different opinion, feel free to discuss. So the reason that I think select the group first, which encourage more balanced expert selection. So it will always force for expert to be for group to be picked first, right? If we directly selecting 206 expert, I think selecting group first, balance group first, then balance the internal expert. I think it will help, right?
Yeah, I
my
think
understanding.
So. Especially because when you are selecting based on the score of the 2 top ones.
Yeah. 2 top expert inside the group, right?
Yeah. So if let's say if there's one group that has the top 2 to be 0.5 and 0.5, and in the other group you have maybe 0.8 and 0.1, there's a chance the first one will get approved. So the second one may suffer. So even the one expert that had a little bit of low score will still get picked because it is in the group.
Correct. It's like a two-level balancing. I feel
Yeah,
this one is
exactly.
more
Higher pickup.
is better. Yeah. Okay. Any other question? Okay. Okay. Then, this part is the derivation for the original nodes is still used in the Deep V3, but in the paper they said they give a very small value for the alpha, so that it won't impact the main model part, right? It still use the ordinary nodes, but give very small value. The main like measure they use is the bias term to balance. So this ordinary nodes, I think we come back later. It's a little bit complicated. This ordinary nodes is from a previous, I think I'm not sure which paper. I think it's switch transformer or something like that paper, but there isn't detailed derivation. This derivation I looked a lot articles, and one of them that is helpful is here. I leave the link here, but it's in Chinese. But because we have like Google Translate, if you are interested, you can translate and have a look also. I think this article is quite good. There isn't much resource on how it's derived, why this formula encourage the low balancing. So we a little bit complicated. We come back later if we got time. Otherwise, maybe next time or something. Okay, then we look the multi-head latent attention. So we replace the feedforward with the mixture of experts, right? Then we use this multi-latent attention, multi-head latent attention to replace the attention part. Let's go through this diagram first. This black circle here, meaning the part that get cached. There is a KV cache, right? KV cache that used in the inference time. So only the shaded part will be cached. So starting from here, hidden input, there are two branches here. One is the query part. The other is the key and the value part. So hidden input. Let's look at this part first. Hidden input then will be down project into a latent representation. This is smaller than the hidden input. Is smaller. Then this will be up projected into into two parts. Up projection meaning that we do a multi-head, right? In the transformer attention, we do multi-head. So originally we just up projection into multi-head, but here we down project first into a latent representation, then up projection to become a multi-head. So in DeepSeek V3, there are two parts. One is the no positional encoding part, and one has position encoding. So rope is the rotary position embedding, right?
Mm.
There are two parts. Then they concatenate together and output the query. So in the original transformer, I think we only hidden state, we up projection into multi-head representation here. So
Yep.
they're directly coming here. But in the DeepSeek, it down project and up project, then concatenate together. And then the rope is like different branch. Here there's no rope part, no positional encoding part, and there's positional encoding part. In original transformer, those are calculated together. There isn't any branch here, right? In this part, do you have any question?
Mhm. Yeah, like from input hidden layer, first you down project. So your original, it's before you do any, like in the actual transformer, what you do is you do key, query, and value calculation for what comes in. Let's say
key query is here, calculate here.
okay, but just before you reach that key query value, you have your original vector that
Yeah.
you're down projecting.
Yeah.
And then what happens after you down project using,
Down
let's say,
project, then we up project. Up
and then
project to become multi-head, right?
yeah, this is a bit unclear how that is happening.
Okay. No problem. The high level, we will refer to this diagram and go through high level workflow later. We only need to understand
Okay.
high level here.
Got it.
We come back later again. So here just the down project, then up project split into two parts. In positional embedding part and the no positional embedding part, then concatenate together. Then this one is the same as the like original attention. So we finally get query, right? Then in the KV part, we doing a similar thing. We here we down project. Down project is same as this down project. And we also when we do down project, we also down project a little bit here for the rope part. You got like image first. We will go to in detail later. So then this part get up projection into multi-head, which include a K part and a value part. But it's a multi-head. You see in the diagram here this means multi-head, right? Up projection. Then this key row, this part has no position embedding. This part has position embedding. They get concatenate together like this one, become a key, right? Then here we do a standard like query K dot product and the weighted sum of value, right? This is the same. Okay, so we got a high level first. Then I split screen. Let's go through this formula first. If you have difficulty, we can first jump into here. Let's try. So with this diagram, let's try to understand the formula that in the paper. So this is the hidden input, right? Hidden input, D means down projection. KV means KV, right? KV cache, KV. So hidden input down project into latent representation. So the formula 1 here refer to the step here. Okay. So hidden input down project into latent representation here, right?
Okay.
And hidden input project and go through rope become this part. So it's this part, right? Project and apply rope, then become this part, right? This is a key with positional embedding encoding, right? Then this key concatenate with this key. This key concatenate with no positional embedding, concat with positional embedding key. So concat here become this. So this concatenate together become this, right? This step is here. Concat together become this, right? So position rope positional embedding part plus no positional embedding part concatenate together become this, right?
Yep.
So the value part coming from this latent representation. So latent representation up project. See here, up project become a value is here, right? Up projection. U means up, okay? Up V. So up projection become this part, right?
Yes.
Here you can see the letter here. T means token. 1, 2, 3 means a head, right? Head. We got a multiple head for each token, right? And this V is the same. So when we up projection, we become multi-head, right?
Yep.
Okay. Let's see the query part is similar. Query part we look at here. So hidden input down project into this latent presentation, right? Representation here. Then latent representation up project into C. So it's here. Up projection into this part, right? Then this one is also got a up projection and applied rope is coming through this branch here, right? So these two are up projected become multi-head, right? Then eventually this part and this part, they concatenate together, become a final multi-head query, right?
Right.
Yeah. Any problem with these two formula? Okay, so I assume no problem. You may ask here, you see these two parts, we down project into latent. We can understand because latent is much smaller size, right? Compared to this latent presentation. You see here diagram, it also means when we see in the code, we will see that this part and this part is much smaller than the previous hidden input. So we do down projection, we can understand because we want to catch them, we want as small as possible, right? But why this query part, they also doing the down projection? Why not just simply up projection, then go through rope and unknown part, right? Do you understand my question? When I going through
why are we doing the latent at the query level?
Yeah, at a query level. That's when I read the paper, I got a similar question. Why we do this? There's a mentioning in the paper similar like this. I just copied out. We also perform no rank compression for the attention query to reduce memory consumption. So my understanding is like this. So this is a little bit smaller. Let me make it larger. So if we directly do how we understand this sentence, right? That's my understanding. So if we directly, for example, the hidden input multiply by direct up projection. So it will become in the largest model 568B, I think. Those parameter is based on that model. So if we put it in, so batch size, sequence length, then hidden the dimension, then if we up project into multi-head, so it has 128 head, and then the head dim is 192. We multiply together. So if we do direct up projection, the up projection metric will be this big, right? This big. When we do multi-head up projection, if we directly do it, then it will require this much memory size, right? Because this metric time together become this large, right? If we do a direct up projection. If we do down projection first, then up projection, we calculated we have two metric here. So this two metric we add together in require this much memory size. I think that's why DeepSeek doing this, right? Reduce memory consumption. Any problem understanding this?
I see.
So this way we reduce memory consumption. Okay, then we go through a high level flow, and we at the same time we look at this diagram so we have better understanding. Can you guys see here? Not very clear, right?
I think it's okay to read.
It's okay. Let me try a little bit more. Here should be okay. Is it okay to read?
Yep, I'm good.
Okay. Okay, this is based on this perimeter is 5885B. So we have hidden input here, right? Okay. Hidden input here. hidden input, we go through the query part first. Query part. So we have batch size, sequence length, and dimension, right? Maybe I make it larger first. So batch size, sequence length, dimension, right? Then we go to down projection. Down projection to become a batch size, sequence length, then Q-LoRa rank. Q-LoRa rank is here. Is 1,500, right? And the original dimension is here. So original dimension is much larger than this one, right? So we down project into this one, the latent representation. Then we up projection into multi-head. So we got a multi-head and the no positional embedding part and the rope part, positional embedding part, right? We up projection into this one, then we split. Then we split into a multi-head, no positional embedding part, then multi-head positional embedding part, right? Then positional embedding part go through the rope to get positional embedding, positional encoding, then concatenate with the no positional encoding part to get a final Q, right? Any question? So if we go back to here, we should now able to understand clearly here, right? We down projection into latent Q, right? Query, and then we up projection into two parts. One is no positional embedding part. The other is positional embedding part. Then go through the rope, then concatenate together to get the final query, right? Do you have any question?
All good.
Oh, good. Okay. Then we go to the other parts. We got input, then we down projection. Down projection into a latent KV plus the rope part for key. You see here in the in here there are two latent here. One is the two parts here. One is the latent KV, right? Latent KV will prepare for the no position embedding key and value path, right? And then the other is this one. This one is prepare for the rope path. So we down project, but we down project into KV latent part plus key rope embedding part, right? Then we split the KV part goes up, and the other part is split out, is the key positional encoding part here. Then positional encoding part go to rope, then repeat. Here you see there's a strange thing here is you only have single head, right? Single head, and the single head get replicated into multi-head, then concatenate. Otherwise, you won't be able to concatenate with the no positional embedding part, right? So here there's only single head here and get replicated into multiple. And the KV parts, we up projection into two parts. One is no positional embedding part, the other is no value part. Then we split into two parts. So no positional embedding key part and value part, right? Then key part get concatenate with the positional encoding part to become final K, right? Key. And we doing the normal multi-head attention. So if we go back to the diagram here, we now can understand that this one, we have higher dimension, right? We mentioned there are like 7,000 dimension here. Then we project into latent and this part, the positional embedding encoding part, and this part split into two, up projection, split into two multi-head, and the other part get concatenate, and this one will expand into multiple multi-head, then concatenate with this multi-head, right, to get a final key.
So the value part is not going through positional encoding at all.
No.
Which is different
Only,
from transformer.
Oh, yeah. Original transformer doing the positional embedding at the beginning, right?
Yes.
Positional embedding is applied in the beginning, but in new models, they are always doing this. So especially when we using the rope positional embedding, we only do it for the query and the key, and it's always applied in the attention block. It's no longer applied outside. I think that's more meaningful.
Because what it says is that when you find out if there is one embedding or one token that has some influence on the other, when you want to find the influence, you want to look at the position, but when you add the influence, you don't care about the position.
Yeah. You want to get a meaning, only the meaning.
I see.
Yeah. Any problem? This is quite important part. No question, right? Okay, let's continue. So the reason we're doing this is to reduce the KV cache. Why we do those like latent down projection? The reason we do this is to decrease the KV cache storage, right? So that we have ability to do the bigger batch size and the bigger sequence length at inference time, right? If we have smaller KV cache, we will have higher capacity, right? So let's see how much we reduce the cache size. So this is I just take from the picture. So in the paper, it compare with all the previous implementations to improve the KV cache, to improve the inference, right? So previously we are doing, this is the original transformer, right? We have multi-head query, multi-head key and value, right? And the number of heads for query key value, they are all the same, right? Then in the group query attention coming from the, I think, I'm not sure if first coming from NAMR or not, but I saw from NAMR. that we group the key and the value paths. So for example, in the diagram here, two of the query only share single head for key and value, right? Two heads from query only share single head. So in this way, we will do calculation later. In this way, because we cache key and value, so this part, if reduced, the size reduced, then KV cache storage will reduce, right? So there's a version that is even more aggressive. So we only have one head of key, one head of value called multi-query attention, right? This is even reduced, only single value head, single key head, and shared by multiple head query, right? Then the latent in the DeepSeek is latent attention. So we down project into this one, right? We only cache this one. We no longer cache this one. We cache this one. Okay. Then we have a look how much in reduced. This calculation is based on single token. And for multi-head attention, let's read through. This means number of heads. This is head dimension. This L is layer, right? Layer. So each token we have n heads. For example, value. We have n heads, and each head has head dim, right? Head dim. Each head has head dim. Then multiply by number of layers. For example, transformer may have six layers. So for this token, it will occupy this much storage times 2 because we have key and value, right? So this is the storage required for each token with multi-head attention, original multi-head attention. Any questions? So I assume you all clear, okay? And then group query attention. We have n groups because we no longer have n heads, right? They are grouped, right? So we only have, like here, we only have 4 groups. We no longer have 8 head. We have 4 group. Four head, shared head, right? So we have n group, and each group has head dimension, and each head dimension, and then we have n layers, which is the same, right? Then we have query and a key, right? So it's 2 times n group head dimension than n layer. So this how these two are calculated, right? Then we coming to the multi-query attention. It only have single group, right? Single group. So one group times head dimension times layers times 2 because we have key and value to cache, right? Then that's this formula. Then the final one is the multi-latent attention. Multi-latent attention, we have split screen. Multi-latent attention, we have n layers and head dim. head dim, these two plus together, and we have line over 2, y9 over 2, that's C. So head dim for each token, the head dim refer to this dim plus this dim, right? So it's the LoRa KV LoRa rank. KV LoRa rank. When we look at here, when we down project here, we have still a little bit small. We have KV LoRa rank plus this part, right? This part. So key position embedding head dim, right? Which is the 2 here. This 2 we want to cache, right? So so KV LoRa rank in the 585, 86, I think, B, it has 512 dimension, which is the 4 times of the head dim. So it occupies 4 head dim, right? Then this is the 4 out of 9 over 2, 4 times of as big as the head dim, and the other 1/2 is from the positional encoding part. It has 64, which is the half of the head dim. So that's why it has 9 over 2 here. So all calculation comes to here. So this part is bigger than this one, right? Slightly bigger than this one, but it's much smaller than previous 2 implementation, right? But the final like performance is saying that it's stronger than this one, but at least as strong as the original, which is good. You see here, in previous if we use group query attention, we reduce some of the model performance, and if we use this one, it's even reduced even further, right? There's a great impact on the model, so we don't want that. We want to keep the model performance, right? But we also reduce the cache, which is very good, right? Any problem so far?
No, we're good.
Okay. I think today, based on the time, we may only finish up to the multi-head latent attention. We will leave this one to the next time. So so let's let's go through a little bit here. Then I think we go to the have a look at the brief code first. Let's have a look at there is a performance improvement called metric associative approach to improve the model performance. Let's see the underlying reason. So when we're doing the metric multiplication, the order matters. Let's see why. The order will affect the calculation and the storage cost. Let's see why. I got a simple example here, right? We have 3 metrics, A, B, C, and each has this much dimension, right? We multiply together. One way is we multiply from right to left sequentially. So it's this approach, right? This approach. We multiply B and C first, then we multiply A with the result coming from B and C. The other way is we multiply AB first, then the result of AB multiply C. Let's see the cost comparison here. So if we multiply AB first, the cost will be AB, so it will be a dot product between the inner dot product between the inner dimension and then the outer time together. So it will be 3 times 6 times 2, right? The cost, right? So each vector, for example, A1 here, A1, the row A1, and the column B1, we dot product here, right? We have, if we have 6 dimensions, so this has 6 elements, this has 6 elements. So dot product has 6 multiplication, right? And 6 minus 1 addition, right? So if we assume this together to be, we call it to be a 6 operation. Actually, in the should be 11 operation, but let's call it a 6 operation, right? This vector times this vector has 6 operation. This dot product, and the total we have 3 times 6 times 2, right? So is 36 operation, right? And then the resulting AB will collapse into 3 times 2, right? So it requires 6 storage, right? 3 times 2, 6 storage. And then we do the result multiplication. Result is 3 times 2 times C, 2 times 5, right? So it has 3 times inner times 5. So 30 operation, right? 30 operation. And the resulting will have 15 storage cost because the resulting ABC is 3 times 5, right? So in total, if we add up the operations and the storage, we have 66 and 21 storage cost, right? Then we do another way, similar, if you can calculate later, but but it has this much operation and the cost, and finally comes to 150 operation and 45 storage cost. So this way is much cheaper, right? No matter is the computation or storage, right? Much cheaper. So the order matters. The order matters. That's why in the DeepSeek code implementation, there are 2 versions of multi-head latent attention. There's a naive version. Naive version which don't care about the order of metric computation, and the associative version has this strategy applied, which reduce the computation cost a lot. And this is calculation I calculated based on I think 685B model. So if we take naive approach, it has this much operations, this much storage cost. For the attention part calculation. And if we using attention part, if we apply this associative trick, we have this much computation, this much storage. There is a great reduction here. And for the final output, the value projection part, if we apply this strategy, it also reduce a lot. You can see here. We will go through the code later. Any questions? Okay. This quite important. So this metric, so the order matters. I think we go through a little bit of code first, then we go through this part. So for transformer, we have embedding, right? Embedding, then number of layers, then this norm and the head, and this one is for the positional encoding, the rope, and this is the multi-token prediction. This one we talk about next time. So this is normal transformer, right? Then each layer consists of blocks. So we have number of blocks, and in each block we have attention, feed forward, right? Then attention norm and the forward norm, right? And in the attention we have skip connection, and we apply the prenorm and go through attention. Prenorm goes through the feed forward, right? This is the ordinary transformer. And this two parts is for the positional embedding, rotary positional embedding. We skip, we only need to know that for now is it will help us to apply rotary positional embedding. If we got time, next time we can talk about this. This one will be a big topic also. So we come to the mixture of experts. We quickly go through the code. I think we go through this way. We're looking at the high-level diagram, and we go through. So this gating parts mapping to this code, this portion of code, and then the expert is the expert here, right? Then MoE is the overall thing. Let's go through briefly. So we have gate, which is this part. We have expert, number of this is routed experts, right? Routed experts is referred to here. And we have shared expert. As mentioned before, a number of shared expert is just a simple MLP layer, but it will scaled by how many shared expert you have, right? It become one thing here. It's not like the routed expert. It's actually individual, right? Like 256 it only has single, but it's get multiplied as you have increased the number of shared experts. So we have the hidden input coming in. Go through this gating paths to get the index, activated expert index. So like top A activated routed expert, right? 8, then for all the tokens in the batch, right? So we get index, then the weight. How much weight for each activated expert, right? For all the tokens. So this 2 is the output from the gate. So this all paths will be inside the gating, right? Gating. So once we have these two, the weights and the index, we can pick the experts according to the index, right? Then we forward. There's a loop here. Yeah, loop here. We will forward the token to the selected experts and multiply it with its weight, right? Its weighted sum, right? The detailed code I will explain at a high level this time. If we do the coding parts, in the later session we will go through in detail. So this part is just picking the already selected experts, then forward the related tokens to those experts, and the experts, because we pick top K and weighted top K, right? We apply weighted top K to get final token result, right? Token result. So this is an overall part, and I forgot this shared expert. Then finally, you see here, and this is the routed expert part, and we have shared expert part, right? Then routed expert part result add to the shared expert, this add, right? Then we reshape to get the final, right? Then we go to the gating parts. The gating parts, we also go through these steps. So gating parts, the input multiplied by a weight to get a score. And the score, we doing the Seek MoE, right? To get a score, then we keep score as our original score. We will look later why we keep it as a original score. And then the score will plus a bias. As we mentioned before, this one is the originally loss-free, right? We introduced this concept, the bias to adjust the score, right? In here, here, right? Then so those codes map into this step, linear with bias, right? Linear with bias. Then we got a score. Score is for the batch size times sequence length, then number of routed experts is mapped to here. Then next part we grouping, right? We just doing a view and grouping into a batch size. Oh, this I think there's a mistake here. Times sequence length, then n groups and n experts per group, right? Reshape it to become this one. then we select top should be top 4 group based on the top 2 expert score inside the group, right? So we select inside the score. Score is already a group and an expert per group. Then we pick top K in this dimension, in the final dimension, right? Top K. So we will pick, this one will reduce into like, once this step will reduce like this, right? Top 2. Then we do sum on this top 2. So it's a top 2 expert score sum together within the group, right? Then we pick top K group out of this group score, right? Group score. So finally, we this is a group index. Selected group index is all the tokens, then top K group. This is 4 in the 4 group, right? In DeepSeek. Okay, so these two map to this select group step. Then we select activated expert within selected group, right? And all of those is to select the activated expert within the selected group. Then we have selected index, which is the final output we want, is this one. Then the weight, but the weight is based on the original score. Why? It's because we don't want a gradient to propagate back to the bias. We said the bias is controlled by the manual algorithm. We don't want a gradient. We don't want a like loss to influence the bias, right? It's like a loss-free approach, right? We said before. So we don't want any gradient to the bias. So that's why we keep a copy here before we apply bias, right? Yeah. So the weight won't. The weight we operate later won't have gradient going back to the bias. Okay, then we just normalize the weight and scale the weight, then return back, right? Any issue so far? Okay, no problem. Okay, this expert, I think we talk next time. This time you just understand it as like feed-forward. It's actually a nice sweet glue implementation. There is some thing to talk about here, but we can talk about next time. Okay. We have 6 minutes left. I think it's not enough to talk about the multi-head latent attention. I think let's finish the MoE part, the expert part. So it's using Swiss glue. I think most native model, most of them are using this one now. Swiss glue is like this. Firstly, we look at this part. This part is called CNU, right? It's called CNU. It's sigmoid linear unit. why is Seek MoE linear unit? Let's see. So we apply a weight linear layer to the input, so we get output, and we use output to multiply its gated value. This is like a gate, right? It's like we learned before the RNN use like Seek MoE as a gating value, right? It's like gate, so it's a gated output. If you suppress some output and suppress and pick some of the output, right? It's a gated value. So this is a signal part, and a sweet glue is just this signal part multiplied by another linear layer apply onto the input. So you can recognize this part like a gated value or more complicated gated value, right? Gated value. So signal is called a switch gated linear unit, right? Gated value. Then this implementation just then project back the result from the signal, right? A sweet glue. Yeah, that's the implementation. Any question? No? Okay. I think we finish here today. I will stop recording, and if you have time, we can talk a little more. Let me stop recording.